Alright, so this is the physics extra credit thing. Problem reads, design charged particle gun that uses a pair of parallel plates with a voltage difference of delta V and plate separation D. Assume a particle of mass 275 milligrams and charge of negative 525 microcoulombs. The launch charge has to clear the obstacle and hit the target. Clear this little guy and hit this guy. Assume the exo hole is positioned so that the charge will exit. Ignore air drag. The unknowns are the delta V, the D, and the angle. So there's all our givens. So up here at the top, all our givens, the mass, kind of a bad picture, but probably still legible. Mass is 275 times 10 to the minus 3 grams, which is 275 10 to the minus 6 kilograms. Charge is just there. Gravity is, we're just using 10 meters per second. We're calling H final in this part 5 meters because this is 5 meters high and 200 meters up far. That's this one. We're using the trajectory formula that I found. So here y is the vertical displacement, x is the horizontal displacement, tangent of the angle launched, gravity, horizontal displacement, 2 times the initial velocity squared, cosine squared theta. So I just plugged in an angle that seemed reasonable, that it would clear this guy and then hit that. And I guess it doesn't really matter what angle you do, because the initial velocity will change to suit that. So I figured 50 degrees seems more than enough to be able to clear the guy, this obstacle, and then eventually come down and hit that. So I just said it's 50, and you solve for the initial velocity, uh, just plugging in basically the values that we have, the 10 meters, the 200 meters or horizontal displacement. The 5 meters will end up being the uh, vertical displacement because we're hitting here and that's 5 meters high. So we say 5 equals all of this stuff. And then you do some algebra and you end up with the initial velocity being 45.545 meters per second. There were a couple more numbers after that, but I don't really care that much. Then just to double check if the particle that we're launching will clear this here obstacle in the middle. Probably will, but we're gonna say y. That's gonna be at least 10. If it's below 10, then it won't clear it. So then we're saying 100 tangent 50 minus all of this stuff. With here we have the initial velocity that we can plug in now, and it's going to be the horizontal displacement's 100 because it's a lot closer. Okay, and then we end up with some 61 meters, so that way clears it. Here we're going to use the conservation of energy stuff, the kinetic energy initial plus the gravitational potential energy initial plus the electrical potential energy initial, spring potential energy we don't care about, equals the kinetic energy final plus the gravitational potential energy final plus the electrical potential energy final. And for here, initial and final, initial we're defining as right at the very start before it's done anything, before the particle is moving or any of that. And then final, we're defining as right when it exits our launch mechanism, our particle gun. The final is no longer over here, it's like right there. Okay. So the kinetic energy initial is 0 because the particle's at rest. The gravitational potential energy is 0 because it's on the ground more or less. It's right down there. The electrical potential initial is QVI. Kinetic energy final is 1/2 the mass times the final velocity, which is going to be this number. Where is it? This number, because this is the velocity right as it shoots off that exits that thingy, and we have no air drag, so it's not going to slow down when we're moving it. Times the mgh. It will have a very, very small gravitational potential energy because as the velocity, or as the final position here of our particle going on is angled, it will have that little itty bitty bit of gravitational potential energy. So we're just going to call that mgh, and then the electrical potential energy is going to be, final is going to be 0 because it's right at the end of the gun. So here we're defining the height final being d theta height final, okay? So we just use sine theta is opposite over hypotenuse. So yeah, that. Solve for each final. And D can be just whatever you want to call it, because D is just that. So I'm just defining D as 0.4 meters. Let's see, my thing kind of got cut off here. Let's see if we can move this up. No, that's not how you do it. Alright. There we go. Kind of works. Where were we? So we're calling the D 0.4, and then that's the height final, so we can plug that in. The only thing we don't know here is the initial voltage, because we have the Q from the problem, we have the mass. We just plug everything in here, ran out of space. This is the gravitational potential using this right here, 0.4 sine 50, because it's going to be the same angle. And then we have, kind of hard to read, the initial voltage is 544.886 volts. That's a lot of damn volts, but it's what we got. And since we're defining, this is the initial, and this is the final, with having 0 final voltage as it exits the gun, that initial is effectively going to be the change in voltage, because the voltage final is 0. So our delta V is 544.886 if we have a theta of 50 and a D of the separation of the plates is 0.4 meters.